everybody. Thank you for attending the Propulsion Futures Beacon webinar today, Industry and Academic Forum on Sustainable Composite Materials for Aerospace. If I can ask everyone to put their microphones on mute, that would be great. That would help with the bandwidth. So it's great to see so many internal and external colleagues engaging with the Beacon in this way through this event. And this is part of an initiative that we have instigated in the Beacon to encourage more industry and academic collaboration through Sitcon funding that the Beacon provides. As I said, if I can ask everyone to stay on mute, that would be great. We will take questions in the end. So if you want to submit your questions as we go along the webinar in the chat function, please also indicate who the question is for. We will also record the session just to make it available on our website for colleagues who are unable to join today. I'll now hand over to Professor David Amabilino, who is the Director of Research in the Beacon, and will be chairing today's event. Over to you, David.
Great, thanks very much, Romina. I hope I'm sharing my screen. Can you just confirm that for me?
Yes.
Yes, I can see
Fantastic.
that, David. Yeah.
Thanks very much. So just to reiterate what Romina said, thank you very much, everyone, for joining us today, and especially for all our speakers who've kindly agreed to present in this topic, which is sustainable approaches to composites for aerospace. What I thought I'd do first is give you a little bit of an introduction to the Beacon and what our objectives are and what that's really about. So the Beacon Propulsion Futures is one of several beacons that the University of Nottingham started a few years ago with the aim of promoting specific areas of research. And our one is lots of things which are related with propulsion systems in aerospace. Particularly, you can see on the slide here on the right hand side, there's a picture of an aeroplane on the right hand side there, particularly aimed at aerospace, but also at other kinds of propulsion systems. And that goes really from, so kind of working top down, if I may. Whoops, let me just go back. Going top down. So our main areas of interest, I would say, are really advanced propulsion systems, hybridization, high density energy storage, thermal management, and advanced electrical machines at the high TRL level, and then medium TRL levels going through thermal electrical machines, light harvesting and electrochemical processes, especially batteries, and then going down to very fundamental things which are related with the materials that comprise these systems. And of course, that's what we're talking about today, new materials that can be invented and can make it into the structures and propulsion systems of aerospace applications. So just to give you a few more details about the Beacon. So as I said, it's funded by the University of Nottingham. We've recruited several postdocs and technical personnel. You can see some of the facilities here. We're also obviously very closely related with the Power Electronics and Machines building, which is being built on Jubilee campus, if you know the campuses of the university. So that's a big initiative that's going on here in the university. We also fund lots of internal projects, and we also fund prime projects. So one of the main objectives from the beacons is to raise funding externally as well. So we provide match funding for those things, and also buy specialist equipment here that's unique to the university and that can help with our research capacity. So thinking about that, those facilities, some of those are in the research demonstrator and accelerator building, which is this building up here. And then we've got all of the things you can see listed there. I think especially thinking about thermoelectric materials and battery materials there, we've got some really new, nice installations going in there. And then there's the Advanced Materials Lab in the ITRC building. There's the liquid processing platform, liquid plasma, processing platform, high energy ball mill and arc melters and resonant mixers and spark massive sintering. And then more kind of fundamental research facilities in the School of Physics, so an MBE machine there, and also equipment for characterization of nanodevices. And in the School of Chemistry, some facilities for characterization of particular materials. And then also here in the university, we've got the nanoscale and microscale research centre, which many of you will know is a multi-faculty facility that acts as a service for all kinds of spectroscopies. And in particular, there's an imaging ellipsometer, which the Beacon funded. So our aim is to connect, collaborate and innovate. So we promote that through targeted seed corn funding, as I said, provide access to facilities and provide in-kind support. And those projects are approved through the Beacon board on which I and Director David Grant sit. And that's the team there, the kind of the governing team as we are. So let's just quickly get to today's topic then. So sustainable materials for propulsion systems is the broader topic. And within this, we're exploring greener materials for propulsion systems and incorporate them with new chemical engineering processes. So those include multifunctional organic and inorganic structures, insulation, conduction, nanostructured composite materials, coolants, membranes, and coatings. And we'll hear today about some of the things going on in the university from some of our academics. And we look forward to those talks. And especially, I'm really looking forward to our guest presentations who'll start now. So that's the end of my presentation. So now, Sarah, if you'd just like to take the helm a second, and I've stopped sharing, hopefully. So let me just admit people in to the webinar because there's people in the lobby. Great, okay. Romina, can you share the program? Do you have it to hand?
David, unfortunately, I can't do that because I don't have the administrative right to, okay. Yeah. Sarah, do you have that, please? Sarah?
Sorry, I was on mute. Sorry, David, what was the question?
Can you put up the program again, please? Thanks. Yeah, so just for the benefit of people who've joined us since we started and perhaps didn't see the program, which we'll just wait to see come up. So I just gave a brief overview of the Beacon, and now right on time, just about. We'll pass over to Luca Restuccia, who from Solvay, and he'll be telling us about Solvay's activity in composite materials, challenges and new opportunities. So Luca, over to you, I hope. If you've got access rights, please take the mic and take the screen. You're on mute. If you're speaking, you're on mute.
Sorry.
It's okay.
I'm back.
Happens to everyone. Thanks
Okay,
very much. Thank you.
Can you see the screen now?
Yes, we can see it. At the moment, it's not in presentation mode. It's as the file.
Okay,
mode.
Just 1 second. Okay, fantastic. So good afternoon, everyone. I'm really happy to be part of this event today. My intention today is really to go briefly through what composites are. Maybe it is not required, but I'll do that. I'll go through some of the traditional advantages, traditional applications, and then expand a bit to some of the challenges and opportunities that that composite bring, and what can be done really to fully exploit these new or potential new advantages to new and exciting applications and industries. So before I start talking about composites, I'll start talking very briefly about Solvay. Solvay is clearly the company I work for. I really wanted to start from this picture that you might already seen. It's a picture showing.
Luca, just a second. Sorry to interrupt. I don't know about other people, but I'm still seeing only your first slide, and it's not in presentation mode. It's in kind of the file opening mode. Yeah. Now we can see it. Yeah. Thank you.
Is it better like this?
I think if you put it in presentation mode,
I was in presentation mode, but it looks like
there is a
lot.
Other people are seeing.
Can you see it in presentation mode like this or not?
Nope.
Have you got two screens? It's probably up on the second screen and you're not sharing the right one, I suspect.
I think, Luca, if you press the little button, you know, where you can sort of make it in presentation mode at the bottom of your screen, you know, where the orange line is, that would put it in presentation mode. You know, when you can minimize and maximize the size, you know, there's a little sort of square shape icon. If you click on that, it would put it in the presentation mode.
Let me see if full screen like this. No,
it's not working. I think you might have to stop sharing the screen, Luca, and go back in. Maybe it's what Steve suggested. Maybe if you've got two screens, you selected a different one. So
no, it's only one, but I always have with this application.
Maybe it'll work second time around. Let's give it a try.
Let me try again.
Yeah, sure.
Okay. Otherwise, if I have problems, you might want to, or Sarah might want to share.
Yeah, let's try one more time, and then
yeah, I'm trying now.
You're not sharing at the moment. Yeah, now it's open, but we're seeing it as the open file, but not as the presentation.
So I think I have some problems here. Sorry.
Okay. Sarah, are you there, Sarah?
Yes, I'm just trying to open it now. I have it as a PDF though, not as slides.
It's the same.
Okay, apologies, it's not allowing me to share it because it's a PDF file.
Okay, look, why not just carry on with this? It's fine. Just scroll down the document, and that will work.
Okay, sorry about that. So my intention was to start from Solvay, really good chemist and businessman that started the company in 1863, starting from a technological breakthrough, the ammonia and soda process. This picture is just a testament of the fact that he was really a science and technology enthusiast. He started this physics conference This picture is showing the 1927 one when leading figures like Albert Einstein and Bohr were really debating about quantum mechanics. But these more a way to introduce Solvay. It's still strongly a family company which has the same focus, the same interest to science and technology, and a strong focus clearly on making science available to a wider audience and improving the level of quality of life and humanity in general. Now, having said that, today's sales around 10 billion euros. We have about 24,000 inmates. A good percentage, a really good percentage of revenues is invested directly in research and innovation, and in excess of 50% of our products are can be considered as sustainable solutions. So in general, sustainability is really a big part of the ethos of the company, and what the Solvay family still wants us to focus on today. So if I go to the next slide, this is giving a bit of a snapshot of the Solvay One Planet goals. It's something that is a big commitment for Solvay to invest in areas where innovation and sustainable solutions is key. But more importantly, it's really structured in three major categories: climate, resources, and better life, with clear goals and measurables that can be looked at every single year and monitored. And I mean, without going too much into details about all of them, but you'll see that there are really challenging targets, especially for what concerns the reduction of greenhouse gas emissions, and has just doubled the yearly reduction versus the 2018. So raising the bar even more going forward up to the 2030. Going to the next now.
Sorry,
yep.
Luca, you're going to have to move down the slides in the file, because at least I'm still seeing these Solvay introductory slides. That's it.
Sorry.
Yeah.
Okay. Maybe you see it now.
Yeah.
Okay. Sorry. So going forward, we can start talking about composite materials now without being too. Let's start with the standard definition. So what they're made of? They are made of two different constituent materials that are consistently, different in terms of physical or chemical characteristics. But when they're put together, they still stay as distinct and separate components, but they act synergistically to create something that has much better and superior performance. So this is a big difference versus mixtures or alloys or solid solutions. Now, in nature, there are plenty of examples, starting from wood, which is made of lignin, and hemicellulose or hemicellulose, as we want to be even more precise. Bones, seashells, granite. So nature has gone there, has already created some optimized structures, which are composites. Clearly, going to engineered composites or man-made ones, simple examples that everyone knows: reinforced concrete, ceramic matrix composites, up to what is more interesting, at least to us, talking about fiber reinforced plastics, and maybe more in particular in this case, carbon fiber reinforced polymers. So if we look today at what are the advantages of composites versus metals, and why they have been and continue to replace metals in multiple applications. Now, starting from the more traditional one, more traditional advantages. Clearly, composites have an extremely high specific strength, which is the strength to weight ratio, and great stiffness. So in general, they have really good performance, but at a fraction of the weight of other metals, such as steel or advanced metals like aluminum. And clearly, this is helping a lot in designing and manufacturing lightweight structures. Now, conversely to what normally happens for metals, clearly they're not subject to corrosion, and they are extremely stable dimensionally, and these are allowing them to withstand really tough and harsh environments. Big changes in conditions from cold dry to hot wet conditions for multiple cycles throughout the life of an aircraft. They are not very prone, or they have no fatigue propensity. Now, in this case, what it means, and we have an example, I believe, at the bottom part of this slide, where there is an infamous picture of an Aloha Airlines 737-300 that in 1988 experienced an explosive decompression and separation of a large section of the top part of the fuselage. And this was, after investigation, it was a problem linked to maintenance, yes, but it was clearly linked to the propensity of the metals to be corroded and to the propensity of the fatigue to create these bondages, the lap shear level, that caused this huge and catastrophic event. Now, going to the next clear advantage, the design flexibility. So, as an example, the B-2 bomber on the bottom right is a good example showing that composite can be deployed in order to provide properties that are not really achievable with metals, and in this case, potentially the ability to evade air defenses, and these thanks really to composite materials. All these technological advantages has helped composite to earn its way into a number of modern applications. When we talk about modern application, I will start from the ones that are really close to our business, or to my part of the business, so aerospace, defense, and space. In this case, the condition and the potential advantages, the traditional advantages of composite that really found a fertile ground, and these where there has been a massive adoption of composites, or a growing adoption of composites over the years. If we look at marine applications, such as in this case, America's Cup boats, for example, these where stiffness and lightweighting are essential, and these where people that is striving to achieve the best level of performance is looking to using composites in order to be more performing in this kind of tough competitions. There is a good portion of composite materials in motorsport and supercars applications. Now, these clearly linked to the traditional advantages I was mentioning before, the lightweighting, but not only that. Is not in some cases. I'll give you an example. Composite have characteristics that are unique. They are really efficient in case of high-speed crashes, and they fail in a really controlled way. And the adoption of composite in some specific parts of Formula One cars has dramatically improved the safety of pilots in the last years. Moving forward, construction. So these were lightweight, lack of corrosion, lack of fatigue are really essential parts, and that's why they're used there. When we talk about sporting goods, the there is a wide array of application there, starting from bikes to hockey sticks, to running sole, to tennis rackets, and these really linked to the ability to well tailor and balance properties, stiffness, and handleability. So essentially, you're giving people using these products a perfect handling, and therefore the ability maybe to have even better performance in their sports. Last but not least, we're talking about wind energy, which is clearly, a sustainable, green, and clean source of energy that is used widely in the world these days. In this case, stiffness and lightweighting is really important, and this is particularly important when we're talking about extremely large offshore blades. But let's see what's next. What can come next. It's really clear in the industry that that composite can be an absolute enabler to multiple frontiers of progress in multiple markets. So starting from electric vehicles, whether they're cars or planes, the ability to make these flexible, very flexible shapes, lightweight, stiffness, are all enablers for vehicles that are currently carrying relatively heavy batteries. Hydrogen propulsion. There have been lots of talks recently regarding the use of hydrogen, especially for aerospace applications. This is where composite can really help. Hypersonics. When we talk about defense, one of the new frontiers of warfare are hypersonic weapons that can fly at 15-20 times the sound speed. These where composites are a big enabler due to their thermal management characteristics and clearly lightweighting. Human air mobility, another great area of development at the moment, with the idea of having in a short period of time, people able to move potentially large metropolitan areas by air, not anymore by car or by going on the road, especially in highly populated regions. Last but not least, another example. The US have recently set very challenging targets, bringing humans on Mars in 2030. Lots of things, lots of technology will have to be developed, but effectively, composite will be a clear enabler when we're talking about also space applications. Now, we have been talking about enablers for new potential frontiers. So what needs to happen in order to deliver this potential? Going beyond the traditional benefits that I listed before in the previous slides, there are a number of other potential advantages that come from the use of composites, which are either not well understood or maybe used in other industries, or in some cases not well utilized by our industry. I can summarize these other potential advantages in two main categories: what we would define as engineering freedom and what we can define as integration. So when we talk about engineering freedom, I like to make in this case an example. So if we consider large commercial aircraft, I believe that the selection of composite materials, for example, for wing applications of 787 or the A350, I think it's clearly something that benefits a lot from the use of lightweight products. with the traditional advantages, but the composites also allow them to create aerodynamic profiles that in reality allow some of these planes to save lots of fuel, between all the other things that are implemented. In general, composites are by definition multiple degrees of freedom. It's the composite, you can really change the fiber type, you can change the matrix, you can change the architecture of your prepreg, you can change the orientation of fibers, you can create different layouts, you can tailor the thermomechanical performance. This is giving designers a high level of flexibility. The flexibility they need to design potentially advanced structures, going one step beyond and potentially trying mimicking what nature does so well, and creating really optimized structure and fully exploiting the potential. Now, when we look at the integration, again, another clear case, it's what is not possible to make with metals can be done with composites. If you are integrating stringers and a skin in a fuselage panel, you're already saving a lot in terms of cost, in terms of number of fasteners that need to be applied versus what would have been done in the case of metal structures. The multi-layer, the possibility of having a multi-layer structure, which is coming for free with composites, is also potentially allowing to integrate other functions. And here, a simple example about the integration of batteries, which are in effect, a laminated structure in its own. So the possibility to integrate new functions into our composite or structural composites. Now, I believe that only a small portion of all this potential has been exploited today. And I'd like to add a bit more to this presentation, talking about what might be the future challenges and opportunities, and focusing only on few of them and not capture them all. But I wanted to start from sustainability today, starting from what in our industry is the perceived dilemma of sustainability. So composites are extremely good products for sustainability in the sense that they are lightweight and therefore they allow for structure to be really fuel efficient. Conversely, and by definition, they are really difficult to recycle, especially when we're talking about thermosetting based composites. So in this case, what are the opportunities? Starting from carbon fibers, there are opportunities to look at biosource or bio-derived precursors for acrylonitrile and polyacrylonitrile, which are clearly the precursor of carbon fibers. And similarly, there are opportunities to look at manufacturing processes for carbon fibers, which are a lot more energy efficient. Today's method clearly require extremely high temperature and times, and energy consumption is not really efficient. Then looking to other building blocks in our composite resin matrices. So there are opportunity to look for sustainably derived monomers or bio-derived monomers, which can be formulated in order to create the right balance of performance. Then when we look at recycling, maybe this is something to discuss later today. At the moment, there is not a really elegant and efficient process, in the sense that when we're talking about thermosetting composites, thermosets are set by definition, it's really difficult to go back to the original component. And a process based on pyrolysis are only eliminating the matrix and they are creating maybe something that can be used for another application, but clearly we're not going back perfectly to the two constituents and to the full level of performance of the two constituents. Last but not least, we can consider opportunities really to start or create new product forms from recycling or from sustainable sources in order to use them for other applications. So, I mean, to give you an example, potentially turning some of the waste streams from this industry or another industry and turning them into usable building blocks. So there are lots of opportunities there. The second one I'd like to talk about today is high rate manufacturing. So clearly the aerospace industry is rapidly shifting toward an industrialization phase, which will require really a leap change in the ability of material and manufacturing processes to meet very high production rates. Materials, in some cases, will have to be capable of very short takt time, and manufacturing processes will have to be fully automated and capable of those rates. So well integration within the cutting, handling, forming, curing, NDT processes in a very well automated process. So to give you some examples about what Solvay has done in this area, Cyclone EP2750, which is a toughened epoxy system, which has been designed to offer some unique benefits to manufacturers, starting from its high rate capability and ability to be used and developed to be perfectly suitable for fully automated process trains. In this case, I'm showing also a Solvay patented manufacturing method called double diaphragm forming process, which is essentially allowing to start from a pre-cut blank and go into a finished part in a fully automated way using a forming technology that was patented, which is actually allowing to achieve perfect parts with takt times as low as 15 minutes. So in this case, these will all lead potentially to reduce part cost, more importantly to parts which have a full aerospace pedigree, so thermomechanical performance and quality, which is equal of aero qualified materials that are currently flying. The last slide I will share with you is looking at multifunctionality. So if we look at how materials were used in the past, we're talking about monoskilled composite in the sense that the only function was to carry load. Today, through all the level of freedom that I mentioned before, there is the possibility to have materials with enhanced and tailored thermomechanical and physical characteristics, which allow to reduce weight and provide some other advantages to designers. But clearly, tomorrow, if we look at what tomorrow will bring, we can actually look at the possibility to add some additional functionalities which are not part of the composite DNA. Am I referring to a number? And here there is only a selection of them. Clearly, when we're talking about acoustic and vibration damping, composites are inherently stiffer, do behave differently versus metal, and these at times can can create discomfort in passengers, in aircraft cabins. Now, some solutions have been developed in that sense in order to mitigate or eliminate that problem. Electrical conductivity is another typical one. Composites are not inherently electrically conductive. They have to be protected against lightning strike, direct and indirect effects. They cannot be used for grounding or bonding. So there are some gaps there, and technology has been developed in order to satisfy a good portion of these needs. Thermal insulation, I believe, this is something that excellent materials, great potential, and possibility to integrate even more. Radar absorption, we have briefly touched before, is really important for military. Composite provide the ability to continuously change the curvature radius. These are an important aspects when we look at the radar signature, but it's not the only one. Composite can bring further advantages through their composition, through their structure, through its microstructure. We have talked about energy storage, so the possibility to integrate that function as part of a structural component. And last, sorry, I had forgotten the structural health monitoring. So the ability to have an airplane or a part of an airplane and to treat it exactly like a human being. Essentially, when there is a problem, this is immediately detected and reported, so that no catastrophic effects are occurring. Very last part. I up to this point I managed never to talk about COVID or to use that word, but effectively, composite can bring and integrate antimicrobial properties without sacrificing in terms of performance or cost or weight. I will conclude my presentation here. I'm sorry about the technical issues, and I'm really happy to take any question that you might have. Thank you.
That's fantastic. Thanks very much, Luca. So I think in view of the time, we'll move straight on. And in any case, we were planning on having the question and answer session afterwards. Luca, if you could stop sharing, and maybe Xianghui can bring up his presentation. Xianghui, can you?
Yes, I'm here. I try to share my screen.
That's great. Thank you. So yeah, for those of you who weren't here at the start, we're a little bit delayed because of some technical issues with the presentation. What I propose is to just go through the comfort break, and we'll just get away when we can, and we'll try and regain a bit of.
Can you see my screen?
Yeah, you're in presentation mode.
Okay, let me try to turn the page. But okay, yeah.
So Xianghui from the Faculty of Engineering, over to you. Thanks very much.
Okay, good afternoon, everyone. Thanks for this opportunity to present my work. I'm Xianghui Hou from Faculty of Engineering, University of Nottingham. Today, my topic is structural design for highly thermally conductive composites. First is a little bit of background. Actually, this topic is related to thermal measurement, because with the industry development, more power density, electrical power density, like a electrical plane, electrical cars, and also this high integration and size reduction of electrical components. So the heat generated from this electrical device become more serious issues will really affect the lifetime and efficiency of the devices. So the question is whether we can produce some materials with very high thermal conductivity, but at the same time with high electrical resistance, because most of the materials, for example, for metal, aluminum, copper, they have very good thermal conductivity, but they are electrical conductive, which cannot be used for insulation purpose. So our idea is try to think about how to change the polymer matrix by adding some high thermal conductive materials. We call it fillers. So the key challenge, as I mentioned just now, the key challenge is not only the high thermal conductivity, but also this high electrical insulation. Normally, for this kind of application, we really need this volume resistance to be around or even higher than 10 to the power 14 ohm centimeter. Because of this requirement, it's really limiting our selection of fillers and matrix and also selection of the process. So our research team this is the advanced material research team. This is our main group, and also involve power electronics, School of Chemistry, and also nanoscale and microscale research centers at University of Nottingham. So the first task is really think about which fillers to be selected. So from this kind of selection chart, what we can find, the most promising candidate is this part. So brown nitride, diamond, or silicon carbide looks like a good candidate, but this value here are more about bulk materials. This value, I cannot see whether you can see my laser screen. Oh, sorry. The value here is more bulk materials, but once they add inside the complex, even it's very high ratio, actually the value we can get is quite low. So the question is about whether we can continue or further make some significant improvement on thermal conductivity, at the same time try to keep electrical insulation properties as required. So once the filler is added in the materials, it really depends on the distribution and how this kind of connection of different fillers. So if we think about, we need high thermal conductivity. So first, we really need this kind of the filler itself can connect with each other. So this one like a bridge. So we can have this kind of protein transfer much smooth and much directly, rather than to have a gap here like this one. And also secondly, about whether we need alignment of this filler or this kind of randomly distribute of filler inside materials. So here it's very straightforward. Alignment, we have more chance to have this more straight functional pathway and also higher efficiency compared to randomly distributed fillers. Think about how to do this kind of filler alignment. So there are different methods can be used. Either use external electric field or magnetic force, or sometimes people even use the shear force method. So if we think about using electric field or magnetic field, under this kind of external force, we have to make our filler itself become electrical field active or magnetic field active. And then we can do something there, but the problem is that when we introduce additional either ions or additional particles that will affect its electrical resistance. So another way is think about using this shear force method. Shear force method, the most popular one is by this melting the polymer or dissolve or disperse these particles inside the polymers, then do this extrusion together. That one can help this alignment of the filler, but one thing is the contact between the filler is difficult to be controlled. So the method we choose is called ice template method, or sometimes also called freezing casting method. So first, we try to produce the dispersion of hexagonal brown nitride. This kind of put this brown nitride platelets inside this water-based solution. So after that, we put this container in a very cold chambers, and at the bottom of the chamber it's cooling by liquid nitrogen. Then we can create temperature gradient from this bottom very low, and top is slightly higher. So because this have very high temperature gradient, so this ice start to grow from bottom to top, and this direction of ice crystal formation. During this procedure, this kind of the particle put inside actually can change or can slightly tailor itself to fit the ice crystal, then finally get this alignment done. So this is how it works. These structures, we called it aerogel. Aerogel, actually after certain treatment, we can get this very porous aerogel structure. You can see here is about its alignment of brown nitride is platelets. Here is an enlarged image along these directions. And this is after that, we can, one way is we can directly do the impregnation of polymer, for example, epoxy. So as you can see here, this is a randomly distributed this kind of skeleton plus epoxy, and this is aligned brown nitride plus epoxy. But that's when we think about this one is like just a physical contact, just now the image is there. So what we can think whether we can make it more solid. So one of the methods we can think is try to do a little bit sintering. So if we sintering this porous aerogel structure, try to link this interface, this boundary more strongly or more solid. Because under this temperature, that's kind of interfacial diffusion happens there. Then we'll link this brown nitride platelet together, and that one will increase thermal conductivity significantly. So here is the data comparison. You can see this one, the black color is epoxy and filled with brown nitride randomly composites, the black color. Then if we change it with a little alignment, you can see the difference. This is with 18% volume fractions. This is one method. Another method is just sintering. So sintering this aligned brown nitride skeleton, especially you can see the temperature at 1000 make a huge difference. It's increased from about 1.2 to approximately to 3. So in order to promote the sintering, so another method is that we can try to add some nanoparticles. So these nanoparticles will stay at the interface of this big brown nitride platelets. Then during the sintering time, this kind of nanoparticle can eventually help this diffusion bonding by these two platelets. So finally, what we can get is this value 3.5 this watt per mK at 32 volume fraction. And also electrical insulation, we can keep this volume resistance slightly higher than 10 to the power 14 ohm centimeter. And we have one publication recently here. So this is one method is mainly for bulk materials. We also have produced another method is thinking about large scale and also flexible like a membrane or a film format. So what we do is we can try to combine a few layers of silicon carbide and brown nitride together. By this kind of design, we can reach a very good thermal conductivity. At the same time, we can also offer the structure with very good dielectrical properties. And this is much better than the commercial polyimide films. So this work is still under development and we have not published. So a particular date, I'm not going to report here. But if you're interested, you can send me email. So here is the conclusions on different two types of thermal conductivity materials has been replicated. And the main story is try to reduce the interfacial thermal resistance of these kind of porous structures, either by sintering method or by additional thermal conducting substance at this kind of joint position. Okay, that's the acknowledgement for the support from Beacon, especially for the equipment for thermal conductivity measurement, and also for the project for the development of this new type thermal conducting composites. Thank you.
Thanks very much, Xianghui. That was excellent. Nice presentation on your work on thermally conducting composites that you're doing within the Beacon. So we'll move on. As I said, we'll take the questions at the end of all of the presentations. So our next presenter is Alastair Stuart, who's also from the Faculty of Engineering. So Alastair, are you there?
Yep, I'm here. I'm just...
That's great. Thank you.
I'm not sure if you can see my pointer on the screen.
That's perfect. You go right ahead. Thanks very much. We look forward to your talk.
Yeah. Okay, thank you very much for for listening to this talk. I am Alastair Stuart. I work at the university. I'm based in the RAD building, which David mentioned at the beginning, and I work as part of Propulsion Futures. I'm also involved in a hydrogen research group, and we look at developing materials for energy storage, predominantly with hydrogen. I wanted to give a little bit of background to why I've chosen this topic today. So you might be familiar with technology readiness levels, and a lot of the work in the university begins at a very fundamental level. So that's down here at TRL 1 and 2. And the idea is that you want to move the technology so it has an impact in the world. So you want to move it so it's developed into a product and commercialized. That's one way of doing that. But often there's a challenge to that. So in my work, we often have a new material that we've developed. We work with a lot of alloys, and we want to test this material, but we only have a few grams of it. And that's all right for some testing. But if you want to think about an application, you might want to explore the potential of the material for a particular function. And to do that, it's quite difficult if you don't have the resources. You may not be able to produce the material in large quantities, or you might not have the opportunity or the time to construct a prototype system. But another way to do that then would be to use a simulation. So that's what I'm going to talk about today. And one of the simulations tools that we use is a multiphysics package. I'm referring to Composite today, but there are other solvers available. And what the solver allows you to do is to think about the physics involved in a process. So I'm showing here specifically to ComSol some of the physical processes that it can model, and you can see there's quite a range. So you can go from electromagnetics through fluids and heat transfer, mechanics and chemical reactions, and you can model all of these processes simultaneously. So you can select from these physical processes what's happening with your particular material when it's being used, and the physics that's been handled simultaneously, and you can combine them together. So it's the methodology that I want to share with you that we use. So the methodology would be the same would be the same for different applications, but you could do a similar approach. So I would begin by characterizing my material. So that's experimentally measuring its properties. I would then construct a numerical model so I could predict the performance of the material in an application, and that would give me a solution. And that would link back to the beginning, because then that would allow me to optimize.
Alastair, sorry to interrupt. We're only seeing your title slide at the moment.
Oh, right. So I have moved it on in presentation mode, but it's not.
Yeah, it's not following, I'm afraid. No.
If I move to here, can you see it now, although it's not in presentation mode?
I'm just seeing a white screen, and I guess other people are seeing that too, because I don't see anything else wrong. That's technology readiness levels, yep.
No. Okay, and if I move to the next slide, does it follow?
I'm seeing technology readiness levels.
Oh, okay. I'm not sure then what's happened with the slideshow. Hang on, if I try it in this format.
So now we're seeing multi-physics approach.
Okay, and if I move to the next slide, is it changing?
Yeah, see that, yeah.
Brilliant. Okay, we'll go in this mode. So I didn't like my previous presentation mode, but I think we're working now. So apologies for that. So just to quickly recap, so I've shown here on this slide the physical processes that are available in this particular package. There are other packages you can use. And there's a list there of what can be applied in terms of the mathematical modeling. And then I think this is the slide I'd got to, so I was explaining the methodology in which you would characterize a material. You would then develop a multiphysics model, and that would give you a solution which would allow you to then think back about how that material would perform in a specific application. So I want to use an example from my own work to do this. So I'm thinking about an intermetallic alloy, and that's in the center of the screen. And you can see that I've suggested a number of experimental measurements we could take to characterize that alloy. So for my particular application, I'm interested in its heat capacity and its enthalpy of formation. So in the top left there, I'm suggesting we could measure that with a DSC. I also am interested in the thermal conductivity, so that could be done using a light flash apparatus. And then this is a reaction of this alloy with hydrogen. We're going to store hydrogen in the alloy. So we're interested in the reaction kinetics and the concentration of hydrogen that can be obtained. So using these experimental techniques, we can characterize the material. So that gives us material properties. I would then set up a model in a solver. And so I'm showing on the right-hand side, I'm imagining my material has been put in a container, a metal container, and I've connected that container to perhaps a hydrogen source. So that could be an electrolyzer. So there is a flow rate of hydrogen coming into the material, and the material is designed to react with the hydrogen so it becomes bonded. And this is a way of storing relatively large amounts of hydrogen in a small volume. So we're thinking about energy density here. So my reactor is described on the right-hand side in the domain, and there is, in the grey is the metal cylinder. I'm only showing, I've sliced the cylinder in two to minimize the amount of computation. I'm showing in the blue domain, which is domain number 2, is the intermetallic alloy, and it's in its powder form. And you know, I'm suggesting for this particular model, there's 160 grams. Now, I haven't had to make the powder to that scale, but my model can predict the performance of it as a powder bed in this container. I've also applied a boundary condition, so there's going to be a transfer of heat. I've got to remove heat from this reaction, and you'll see why in a moment. On the left-hand side, on the top left, I've got the model tree, and it's showing that there's material properties have been entered. So that's the material properties that we characterized in the first part of this process. And then I've selected some physics. I'm interested in heat transfer in the porous media, and I'm also going to think about a chemical reaction being solved simultaneously. So that's the hydrogen reacting with the alloy and becoming bonded with the alloy. And then I've shown down below, the last table here is just some of the properties that we obtained through characterization is now part of the solver database. I then go on to obtain a solution. So you can see on the left-hand side here, the solver has predicted what will happen as the hydrogen transfers into the container. It reacts with the alloy, it becomes bonded with the metal. And as it does so, the concentration of hydrogen in the alloy is increasing. And that's this blue curve that I'm showing over time. I've called it hydride fraction, but it's essentially the concentration of hydrogen. And you can see it has a particular shape. What's happening in the container? Well, there's a temperature difference in the container. So I've given you a plot of that, and you can see through this temperature scale that it's hottest in the middle. And then as we get towards the walls of the container, it's reaching the cooling temperature, which I think was about 20 degrees, about 290 Kelvin. And the solver's then revealing to me in this application how the material will perform. I've not had to make the material, I've not had to build a prototype, but I now have some idea, so long as my inputs have been correct and I've used the physics correctly, I have some idea of the potential of this material for this application. And I can see here that there's an issue of heat transfer. This reaction is like very slow, and I might be trying to meet a certain rate of hydrogen hydrogenation, because I'm coupling this container to suggested perhaps to an electrolyzer. So I can then think about how I to improve this. So for this example, I'm going to use some fins. I'm going to make them out of EcoFit F, which is an expanded natural graphite. Fortunately for us, the manufacturer has done the characterization of the material already. So I'm showing some properties here of it. And the important properties for us at the moment are in the middle. You can see thermal conductivity at 20 degrees. And in the plane, it's 190 watts per meter Kelvin. And through the plane, it's 5 watts per meter Kelvin. So I can embed that into the solver now. I can introduce that as a new material. And the next slide, I'm doing that. So on the right-hand side, you can see my container. These grey partitions are the fins, and they're embedded through the powder bed at 8mm intervals. And I have identified them as a new domain. So domain number 3 is the EcoFit. It's now part of the model. And the solver will now run the same simulation, but it will run it with the introduction of fins. So if I go to my next slide, you can see the impact of those fins along with the alloy. So I'm using the same alloy, and I've plotted both curves here. So the original curve, when it was the powder only, is in blue, but we now have a new curve in green, and this is where we have introduced some heat management in terms of the fins. So the fin properties are enhancing the thermal properties of this hydrogen store, and it has accelerated the speed at which the reaction takes place because it's managing the heat. The heat's allowed to disperse to the surroundings of the store, and we've got this much faster reaction taking place. Again, I've shown the cut through for temperature just to show you that you can interrogate the solution and you can get all kinds of insights in the solution. It's a three-dimensional solution, so that helps you to visualize what's taking place in terms of heat. And you can see we still have hot spots within the powder, but where the fins have been placed, they are performing the role of a thermal bridge to the outskirts of the reactor. So we've done this without actually building the prototype. We haven't had to make more material. We've pursued a simulation, and we've used the material characterization to build the simulation. And this is quite a small, this is quite a basic representation. You could have much more complex geometries, and you could dream up some quite involved scenarios, but the methodology would be the same. So just to recap then, what I've said is that you may see a multiphysics solver as a way of exploring the potential of a material, and this could cover all aspects of physical processes. It could be mechanical, it could be electrochemical, it could be heat transfer, and it could be a combination of all of these. And in my example, I was combining heat transfer with chemical reaction, but you could get quite complex simultaneous solutions with this method. Characterization of a small sample of the material allows you to predict or explore the material's potential in a larger system without having to commit time and resources to building the system. And that was the methodology, those 3 steps that I followed. There are some limitations, and that's quite important to recognize those. So the numerical model is limited to the material properties that you've measured under certain conditions. So for example, the graphite, expanded natural graphite that I used, its properties were at 20 degrees. And I'd have to make an assumption, or I'd have to ask the manufacturers, do those properties change if my store operates at, say, 100 degrees? So there are limitations you have to recognize in terms of how you gain your material properties. The other limitation that is quite important is you're extrapolating the material behavior onto a larger scale. And it might be when you increase the scale of that system that other properties occur that you're not anticipating. And this is a real problem that we have come across in our own work. So there's a caveat there that although you're simulating a larger scale system, you have to be wary that there are other behaviors that might occur that you're not going to glean from your characterization. And finally, really that there is a 4th step to this. I've only shown 3, but the 4th step would be then to validate it. So if you see the potential in the material or the application, you might then be able to secure some interest and then move it into a 4th stage where you actually test the model against experimental data. So you would be building a prototype or a proof of concept system. So that ends my talk there. Thank you very much for listening. I want to thank Propulsion Beacon for allowing me to present today, and for all of you for listening.
That's fantastic. Thanks very much, Alastair. So we had a comfort break program now, but we're a little over time because of the technical issues that we've had with some of the presentations. So sorry about that. I'm afraid these things happen with Teams presentations sometimes. So we'll move straight along if that's okay. So our next presentation comes from the company BNNT. And we have with us Roy Whitney, who's the president and CEO of BNNT, and Lyndsey Scammell, who's the product development manager there. Roy and Lyndsey, it's a pleasure to have you with us, and I hope you're going to be able to share your screen. Okay, let's see. Fingers crossed.
Yes, thank you.
I can see a screen beautifully. Yeah, could you just try going forward and back? This is the.
Yeah. How about that?
Yeah, it works. That's great.
Oh,
okay.
beautiful.
Over
Okay.
to you. Look forward to your talk.
Well, David and everyone, thank you very much for the invitation. Lyndsey and I appreciate the opportunity to share what we're doing with BNNT as we are developing boron nitride nanotubes and various multiple forms for multiple applications, many of which relate to aerospace composites. Next, and Lyndsey and I'll jump back and forth a few times. Lyndsey, please go ahead.
Thanks, Roy. So as he mentioned, we manufacture boron nitride nanotubes, which are the boron nitride analog of carbon nanotubes, which you might be more familiar with. BNNT is being experimentally discovered in 1995. So you might be familiar with these more carbon sorts of crystal materials, diamonds, graphite, and carbon nanotubes, BNNTs being the one-dimensional analog. So they're made of alternating boron and nitrogen atoms and have a corrugated surface. And the BN bond is polar in the boron nitride nanotube, which is largely responsible for the difference in properties between the carbon nanotubes and the BNNTs. BNNTs are electrically insulating. They have a band gap around 5.5 eV, which is largely unchanged by the morphology or the chirality of the tube itself. Next slide. So on the right side of this photo here, I'm showing our standard product 10. This is the as synthesized boron nitride nanotubes in what we call a puffball form. The dark color comes from the presence of some elemental boron, which is one of the two byproducts of our synthesis method. We can refine the material, as you can see here in this jar on the left side. It has a nice white appearance, and that is contains about 50-50 of boron nitride nanotubes and nanoscale hexagonal boron nitride. We can also process this material into various form factors, dispersions, powders, or what we call mass, which are just the sort of BNNT analog of a carbon nanotube bucky paper. What we've been working on in the last year or so is to further purify our standard product to remove that hexagonal boron nitride. So you can see these are a couple TEM micrographs I have here. You can see sort of the nanoscale bits of hexagonal boron nitride that we're trying to remove to generate what we're calling SP10RX, which is a highly refined material that is more nanotube rich.
So this gives you a little bit of the history. As Lyndsey mentioned, the nanotubes were first really discovered in 1995 at Berkeley Lab, and they were moved forward by a number of developers, but the big breakthrough came in 2009 when the team on the left on your screen there, of Mike Smith, who's our chief scientist now, he was at NASA at the time, and Kevin Jordan on the far right, who is our chief engineer, and he still works with Jefferson Lab, and Joel Park, who was at NIA and now is at NASA. And what they're being recognized for in their centennial year as the invention of the year are these nanotubes. And because this was a significant achievement that NASA and DOE put a significant investment in to make happen. So what we have now is we have the first and only commercial facility that's non-government. So some nanotubes are made at other facilities, but we're really the only commercial facility doing this. We also have the first and only pilot plant that we brought on this year. So we now run multiple rigs in production, multiple shifts, and we can tailor many of the materials. As Lyndsey was referring, we can take them to different stages, and we have different synthesis parameters that come up. So overall thing that you asked for, I know, David, when we first chatted or a little bit back, was how efficient is this? Well, we've moved from $50 million lasers where the advanced techniques came down to very commercial things with modest CapEx, and we have the most efficient production and the highest rate per unit energy of anything that's going on at the moment. So we have collaborative agreements with NASA, we have collaborative agreements with the Department of Energy, and we have Office of Naval Research, SBIRs, and CRADA. So very engaged with the community that where this technology advancement came out of. Next. So this slide represents why did NASA get interested in this? So it's a bit of history, and they, Charlie Harris, their very senior NASA administrator at NASA Langley Base, did a survey and looked at all of the materials that they could do advanced aerospace components with, and then asked the question, what survives at high temperature? And there's really only those 3 out of all the ones they initially looked at. This is back in early 2000s. And BNNT is one of them, and it's one with this spectacular strength and modulus. So this built their interest and justified that they invested funding in this. So NASA's been with us for almost 20 years, thinking that this is a way to get to aerospace vehicles of interest. Next, and I think that's yours, Lyndsey.
So boron nitride nanotubes have a very high strength to weight ratio, making them very useful for aerospace composites. They can make those materials more lightweight. They can increase the surface temperature because of their high oxidation resistance, make parts more durable, increase their lifetime and wear resistance. So what we're working on is, as Roy mentioned, both partnering with our collaborators and also doing work in-house to support a lot of composites work, as well as neat structures such as fibers and yarns. So composites might include metals, polymers, and ceramics. On the right here, there's a few photos I've shown, example of a powder that we've made from the boron nitride nanotubes, so that it disperses really well in a epoxy resin that was of interest to someone, so that they could make some different glass fiber reinforced parts. Those are some dog bones there you can see cut. There's also a lot of, we talked a little bit about multifunctionality today. BNNTs have the ability to kind of be that next gen material because of this host of different properties they have, in addition to their strength, their thermal conductivity, low CTE, oxidation resistance. They're electrically insulating, and they also have the ability to contribute to radiation shielding. So starting out with metals here, to talk a little bit about some work that's been done with material that our company produced, is some work with titanium MMCs out of Florida International University by Arvind Agarwal. He used a unique method to actually disperse the boron nitride nanotubes in titanium. I used a ultrasonic assisted dispersion method to get the boron nitride nanotubes here coating and sort of at the interface of those grains. And then he explored different sintering temperatures. So here is a stress strain curve of a lower temp and a higher temp sintering process. And he saw that the higher temp process actually gave him better results. And they attributed that to the presence of some of these actually byproducts of sort of decomp byproducts here at the grain interface, but that actually was what helped the bonding of the tubes to the Ti64. So that's some recent work out of there in 2020. And then also there's been some work on aluminum by Hitachi Metals in Japan. This comes out of a patent a couple years ago. This work was actually not performed with our boron nitride nanotubes, but I still thought it was interesting to include. Aluminum's of interest because of its low melting point. So they actually created a method to scalably cast a BNNT reinforced aluminum MMC and had some improvements in the modulus and tensile strength. And then to move on to polymer composites, we have a collaborator with the Navy out in China Lake, California, who's working on electrospun fibers, particularly PAN, which of course is a precursor to carbon fiber. So they're working on using a kind of unique dispersion method to get the loading of the nanotubes up in PAN and then to electrospin that. As you can see, of course, as you increase loading in something like a fiber, right, you get more tube-tube interactions, and you're going to have a higher strength fiber that is going to be able to display more of those favorable properties of the BNNTs rather than having all these voids, as you can see here. So what they reported here a couple years ago in 2019 was the observation of this percolation threshold. So this is strength and this is concentration of nanotubes. And if you follow this black curve, you can see that at some point the properties start to improve dramatically. And that's what they're working on now. And they've actually, I think, improved this weight loading even further beyond the 20%. Another example of some work with polymers is out of the State University of New York, Binghamton, Xianghui Hou. He's actually doing some more fundamental work to understand the interface strength of a boron nitride nanotube and a polymer. So he actually explored the shear strength of BNNTs in epoxy and PMMA by using a really neat method using an AFM probe and actually pulling out individual nanotubes and measuring the force that took. And they found that the BNNTs had a really high shear strengths, and they attributed that to the van der Waals and Coulomb forces at the interface, and found suggested that their BNNTs are a great structural reinforcement for a nanofiller for polymer matrices. Something else we're working on in-house is thermal management. So boron nitride nanotubes have extremely high thermal conductivity and electrical resistivity. So on this Ashby plot, they would be way up here off the plot actually. So we're partnering with some different collaborators and also doing some work in-house. As you can see here, we've got our this is a ASTM D5470 thermal tester, and we're making different TEM materials, thermal interface materials, and testing them, as well as also working on some anisotropic thermally conductive fibers to use as reinforcements for those. This is work funded by the Office of Naval Research, and we've had some very favorable results so far by adding just small amounts of boron nitride nanotubes to different composites.
So to summarize, emphasize, we have a pilot plant in full production. We can tailor these forms of materials so that we can adapt them to make things that are best for putting in various composites. Different composites actually prefer different fibers and different materials, and we can get them into fibers at this stage to some degree. And these are all active R&D components, and we are actively working with multiple collaborators to advance these technologies now that we have the capability of supplying the material in the quantities needed to do the type of advancement in TRL levels of great interest to people who are looking to get to final products. Lyndsey.
Yes, so we're pursuing all kinds of specialized applications for nanotubes, filling nanotubes, which might be because we're actually found that some of our new processing methods are actually able to open the ends of the nanotube. So that's sort of opened up a new world of applications for us, as well as composites, additive manufacturing. It seems like aluminum is going to be really interesting material because the BNNTs do survive the casting process, and especially the thermal conductivity, thermal management project we're working on as well. So I think that's it. Thank you very much.
Yes, and we'd also like to in particular thank Professors Andrei Koboleskov and Graham Rance, who work with them, who we've been able to work with multiple years there at Nottingham on a variety of projects of special interest, which I'm sure you can speak with them. They've developed some of this technology that we're interested in. So we appreciate that opportunity, and we appreciate the opportunity to share with all of you. Thank you.
Thanks so much for your presentation, Roy and Lyndsey. I hope you can stick around a while till the question session. Is that okay?
Yes.
Yeah.
I think we're fine.
Oh, that's fantastic. Thank you. Because we've got two other presentations now, so they should be 10-minute presentations. So the first one is from Thomas Turner, who's going to talk to us about challenges in carbon fiber recycling and reuse. Hi, Tom.
Hello.
We don't have a share nightmare.
Yeah, let's see if I can cross the first hurdle.
Yeah, right.
Okay, how's that?
That's a great, yeah, perfect. Wonderful.
Amazing.
Thanks.
Okay, well, thanks very much for inviting me to speak today. My name is Tom Turner. I work within the Composites group here at the University of Nottingham. And I'm going to spend 10 minutes just talking through some of the challenges associated with sustainability and high performance composites, particularly for aerospace structures, and then show some of the work that's going on here at Nottingham, which hopefully provides some solutions to some of these challenges. So very grateful to Luca for setting the stage very nicely at the beginning and talking about some of the big advantages associated with composites in aerospace. And he alluded to some of the complexities of recycling and reuse. So we'll talk about those a bit more now. So where are we from a sustainability perspective in aerospace composites? We're talking here primarily about carbon fibers embedded in an epoxy matrix or other high temperature thermosetting matrix. And there's really strong motivation to use these materials, as we've heard, because the potential weight save in aerospace structures is very significant. Historically, aerospace hasn't really had to cope with massive legislative pressure in terms of sustainability, whereas now we do see an increase in pressure and public perception of the sustainability issues. So it's fair to say that within composites, things are ramping up, and more people are getting interested in looking at composites recycling and reuse. The sort of materials we're talking about here are varied. You know, there are many different waste streams that come from both production scrap and end-of-life parts in aerospace. And what we'd really like to do is do something with those materials to reuse them. So the sorts of waste streams we have over here are things like time-expired prepregs, in-process scrap from cutting and nesting operations to remove the plies from a roll of material, three-dimensional cured offcuts. You know, most composites processes are not net shape. We've got some trim area that we're removing, and then we'd like to recycle. And then last but not least, end-of-life parts from scrap aircraft. These could be very large. There's huge intrinsic value in those parts. You know, they have a lot of very expensive material in them, but as we've heard already, it's very difficult to recycle those materials. So recycling processes have been around for quite a long time, and it's only really now that we're seeing this sort of snowball effect in ramping things up and getting things going in this industry. So certainly we've been working on composites recycling here since the mid-90s. My colleague Steve Pickering has been very active in that area. I think in summary for the context stuff, carbon fiber is really difficult to recycle and reuse. Carbon fiber itself is a very energy intensive material, equal or perhaps even worse than aluminium. And so it's a difficult area, but aerospace is a very interesting field in some senses, in that the use phase of an aircraft outweighs every other phase by a very long way. So if we can save some weight in an aerospace structure, that will pay for itself from a sustainability perspective in reduced fuel burn in a matter of hours. So in automotive, we might worry about the car getting to 50,000, 100,000 miles before we get environmental payback for the use of lightweight materials. But in aerospace, it comes very, very quickly. If we can save weight, we're doing well from an environmental perspective. And that might mean using materials that are perhaps not the most environmentally friendly, sustainable materials, but we need to adopt a sort of life cycle approach and think about the use phase, which, as I say, is really dominant. So our focus really here is looking for solutions of how we can reuse materials that come from primary or secondary structure in aerospace. So can we reuse them internally within aerospace, which would be really nice, in things like interiors or tooling? And you'll see a couple of examples on this slide of a seat back demonstrator that we made with Boeing a few years ago, and a galley door panel demonstrator. These are nice applications, but they're not really going to reuse. They're not going to get back the full volume of material that we have, which is going to come out of aerospace one day. It's not going to reuse that back into aerospace. Tooling might be another opportunity where there are large parts which don't have enormous structural requirements. We may be able to use some fibers there. But another opportunity might be taking carbon fiber from aerospace and putting it back into automotive. And that might really help us because automotive are struggling from a cost point of view with carbon fiber, even though they like the weight save potential, and also a general shortage of material. So there is an opportunity to reuse carbon fiber composites from aerospace back into automotive, and then we'd be looking at something like an aluminium replacement sort of material. So the big problem with composites recycling is that the form of the material changes from the virgin material, which looks something like this, sort of several kilometers of fiber on a bobbin, which you can put into your manufacturing process. When it comes out of a recycling process, it's going to look something like this on the right-hand side. So we're going from something that costs maybe 20 to 50 pounds a kilo for typical aircraft grade fibers, and we're recovering something that's only cost a few pounds a kilo, but has a really different form. So it's not like aluminium recycling or glass recycling, where the material that comes out of the process looks like the material that went into the process. We can't recover continuous fibers. And so the fibers that we do get are short, they're a variable fiber length, they're really fluffy, and they're quite entangled. It's a bit like black cotton wool, but a bit itchier. So what this means is that we're not going to be making aircraft primary structure from recycled fibers, because aircraft primary structure is really reliant on having unidirectional continuous fibers made up into layers, and we're just not able to restore that form of product and get that back into new aircraft. So this raises some tricky issues for us when we think about recycling and reuse. So just to show a couple of things that we've been doing at Nottingham, quite a few different areas. One of my colleagues, John McKechnie, is very interested in life cycle modelling, and so has done a lot of work into this, taking material from one area and reusing it in another. Over the years, we've developed several recycling processes, so a process to actually get the fibres out of end-of-life composites or in-process scrap. And what you can see here on the right-hand side is one of those processes, the fluidized bed process. This is in our Aerospace Technology Centre, a photo taken a few years ago of a rig that we built in collaboration with Boeing to demonstrate this process to sort of TRL 5 or 6. And we have developed some other processes which can recover resin constituents rather than just the fibres, but there's no work on those at the moment. The area I'm really interested in is this reuse area. So it's one thing producing the fibres, but how do we go on and get them back into materials that we can use again, preferably in processes that are already established and understood. So the difficulty there is coming up with a suitable format, an intermediate format that we can get back into components, maximizing mechanical performance, minimizing energy in terms of added energy, to turn that fluffy ball of fiber into something that we can actually use. And so a lot of the work is scale up, technology readiness assessment, and effectively business case development, looking at energy and automation and how we can make these fibers for a low cost. So the biggest problem with these fluffy fibers is that they have excessive loft, a bit like cotton wool. If you squeeze it, you can't really achieve that high packing fraction of fibers that you want in order to make a high performance material. So typically you would want about 60% fiber volume fraction. And if you just take recycled carbon fiber and squeeze it, you get about 10%. And if you squeeze it really hard, you might get 20, but then you're starting to break the fibers and reduce your mechanical properties that way. So we think that fiber alignment is a really key enabler. So we've developed a process here that disperses the recycled fibers in a liquid, and then we use a hydrodynamic effect, a sort of convergent flow process, to realign the fibers and make them look a bit more like this in top view, or this in side view. So we're looking at fiber alignment not really to get higher performance in this direction than the transverse direction, but to get higher packing so that we can get more of these fibers into our composites. But cost and energy and labor added through that conversion process are a big challenge. So that's a very quick introduction to some of the stuff that's going on here. I'd be very happy to talk to anyone about it at a later date. But where are we going next? I think probably we're going to see an increase in pressure to increase sustainability for composites. And certainly we see more projects coming through looking at this area. Personally, our goals are to scale up these processes to determine energy cost whilst sort of doing incremental enhancement to make the gap between virgin carbon fiber and recycled carbon fiber from a performance perspective even lower than it is. But there are some really big problems associated with commercialization. At the moment, we're sort of stuck in a bit of a rut where there's this increased perception of a big problem in the future, but it's not really reflected either in quantities of material coming through for recycling or R&D spend. And so we're just sort of on the verge of, or on the cusp of a solution. The technology solutions are probably there. It's just a case of funding and scale up, and maybe getting something into a large scale automotive solution that might sort of trigger further research. Thanks very much for your time. Happy to answer questions at the end.
Great, thanks very much, Tom. Yeah, I'm sure there'll be some questions at the end. We've just got one more talk coming up, and then we will go into the question and answer session. So please go ahead and think about some questions for our speakers. Our last presenter is Tanvir Hussain. Tanvir, if you want to take the reins. I'm sure you're used to Teams and there'll be no problems. Now the pressure's on.
Let's see whether it works or not.
Yeah.
When it comes to screen sharing. Is something happening? Can you see the screen?
Yeah, I can see your first slide.
Okay. If I move something, can you see the slides changing?
Yeah, that moves.
Brilliant.
Brilliant. Thank you so much, Tanvir. Go ahead.
Brilliant. First of all, thanks very much for having me here today. So my name is Dr. Tanvir Hussain. I'm an associate professor in materials engineering and coatings technology. I was listening to the presentation on boron nitride. So in my next 10 minutes talk, what I'm going to try to do is give you some ideas about what we are doing to make metal composites and ceramic matrix composites, mostly for propulsion's activities. So first of all, just lay out some sort of pictures of what we're looking at. So surface engineering and advanced coatings are quite a big thing in the UK. It's roughly around 11 billion business, and it affects products that are around 140 billion. So CMCs or MMCs, ceramic matrix composites or metal matrix composites, they're widely used in aerospace propulsion, space, defense, civil aircraft, and lots of other related technologies. The gas turbine industry, we're producing around 228,000 turbines, and every single turbine has got applications for these composites, and they are critical for the functioning of this. One of the downside of that is also the transport. The aerospace sector produces around 915 tons of CO2, and that's around 12% of CO2 coming from the transport sector. So for the aerospace or the propulsion in general to be greener, cleaner, and sustainable, we need new materials, new manufacturing processes. And one of the ways we can do it is a broad group of technologies called thermal and cold spray. And globally, the thermal spray coatings industry is around $13 billion. So what we're looking at, this is a center of excellence at Nottingham University. This is part of Propulsion's Future Beacon. So this is a brand new facility with 3 spray booths, one for all combustion-based systems, anything which burns like a small rocket engine, another one for a plasma, temperatures got as hot as the surface of the sun, 10,000 degrees Celsius, another one for cold spray technologies. As I go through my presentation, I will give you some examples of how we have been using this for making metal matrix or ceramic matrix composites. So there are 3 technologies I'm going to cover, and this is a my starting point for all sorts of particle-based systems. It's a temperature and it's a velocity here. That's where plasma sits. The particles are really, really hot, but the velocities are quite low. So in a plasma, I've got a tungsten anode and a copper cathode, and a DC current is producing that plasma. We're injecting powder with nanomaterials, with liquids, with solids. We're developing a coating, couple of 100 micrometer to several millimeter thick, as also an additively layered manufactured coating. In the combustion-based system, high velocity oxyfuel is an example. It's essentially a small rocket engine where we're putting oxygen and hydrogen, and it's producing a supersonic gas jet, and powders are being injected to produce that surface. And the third one is a cold spray. And in cold spray, we have no melting, but we are simply using the acceleration of a gas in a convergent-divergent nozzle. We're introducing powder particles. They are building up layer by layer like in additive manufacturing without any heat. So we have now installed an axial suspension plasma spray. You can see the picture here, that's a robot and that's a suspension plasma. It's a beast. It's a 750 ampere power supply, and it can produce microstructures which are like columnar feather type structure. And these are highly desirable for aerospace application. That means these are strain compliant. So when you heat it up, they expand, and when you cool it down, they shrink. So it produces a unique microstructure and composition, which is not possible through any other processes. I'm going to touch on this a little bit on ceramic matrix composites. So the other associated technologies we're using is the combustion-based system. So you can see the supersonic jet here, and these are the particles being injected. That's here we're doing axial injection. Particles are getting really, really hot. Here we are doing radial injection. In this particular case, we're injecting a carbon nanotube carrying suspension, and the suspension is breaking up in the flame to produce that structure. So let's look at a couple of examples of ceramic matrix composites. So ceramic matrix composites, the matrix is made out of either a carbide or a nitride or an oxide. In this particular work, we have been working on it for the last couple of years now. We have chosen aluminum oxide, a relatively cheap but versatile material. And we have added, using the suspension thermal spray process, 1 weight percentage of graphene nanoplatelet. That's the cross section of the structure, and all of these dark bits are the reinforced material. And that's a fracture surface. When we have fractured it, we can start seeing those graphene nanoplatelets or GNPs, they are embedded in here. One of the challenges of ceramics is fracture toughness. Ceramics are brittle. But by adding the graphene nanoplatelets here, we can increase the fracture toughness quite significantly. That's for alumina, and that's for alumina with graphene nanoplatelet reinforcement. We can also increase the hardness. And these 2 graphs at the bottom are showing its performance properties. And here, this is how alumina performs in a wear test. It's a standard sliding wear test. The amount of material we're losing is in millimeter cube over Newton meter, around 10 to the power minus 4, 10 to the power minus 5, that sort of range. When we develop these ceramic matrix composites, it can drop by 2 orders of magnitude. And these are for applications in propulsion. It's a significant cost saving for the same material with a small amount of cheap carbon-based systems. Similarly, for coefficient of friction, we can drop the coefficient of friction from around 0.5 to around 0.3. And what that means is it means energy savings, because you're not wasting your energy by producing friction and as a consequence heat. Moving on, another example. So these are all published work. I put the paper links at the bottom and the slides will be made available after the talk. Here we are working with chromia, so chromium dioxide, Ca2O3. A lot of aerospace components used to be coated with hexavalent chrome, but because of REACH regulations, chromes are no longer allowed from electroplating side. So what we're doing is we're developing chromium oxide with graphene nanoplatelet, and then we spray them using suspension HVF, and that's how we get the GNPs built into that chromia. And what it does, it can lower friction by around 15% in that system, and wear rate on the coating by 20%, and on the counterbody, in this particular case in alumina, around 70%. So by making simple composites based on ceramic, the performance can be enhanced significantly. So these are some of the microstructures, scanning electron images, showing you the robustness and the uniformity of these coatings. Second part of the presentation is about metal matrix composites. So we work a lot with MMCs, and MMCs are quite useful for a lot of applications where you want ductility from the metal and you want the hardness and the toughness from the ceramic. So one of the things we use at Nottingham is called cold spray additive manufacturing. So this is a high pressure cold spray setup, goes up to 35 bar. And this is a low pressure cold spray setup, which is around 6 bar. In a high pressure cold spray, we inject the powder and heat the gas up when you're using cheap gas like nitrogen. And these particles travel in excess of 700 meters per second. When they hit the substrate, they deform and stick to each other. Similarly, in a low pressure cold spray, we also add a ceramic component. And when these particles exit the nozzle, it then starts producing that metal ceramic mixture. You can start making several millimeters thick deposits using this cold spray additive manufacturing. This is an example. This is an unpublished work. Here we were developing MMCs with aluminum magnesium with alumina powder. So here my reinforcement material is alumina and the powder is a gas atomized aluminum magnesium alloy. So there are two sets of examples here. One is an aluminum 7 magnesium weight percent. Another one here is aluminum 10 magnesium. The darker phase, that's the coating microstructure here, and that's the substrate. The darker phase here is ceramic and the brighter one is metallic. And you can see the uniform distribution of these structures. By using cold spray, we can reduce the porosity of these MMCs to around 1%. So they are really dense, useful MMCs for lots of application. This is just to give you an idea of their performance. Sort of wear rate wise, specific wear rate, we are around 10 to the minus 4, and for this one is around 10 to the minus 6. So they are significantly better than just the pure metal or just the pure ceramic. My last example here is we were developing MMCs here with titanium carbide. So we had commercially pure aluminum powder, and these are titanium carbide particles laced around. And we sprayed it using cold spray. And what happens when we do that? Some of these particles, the titanium carbide reinforcement phase bounces off and doesn't contribute to the coating or material deposition. We can also do another technique called a satellited process, where we make the satellites very similar to one of the presentations you've seen from Florida International University's work there, where we have got titanium carbide around those metallic particles, and we can then spray it, and that's how we can incorporate the ceramic into that MMC. And when we do that in satellited system, our retention is around 12%, and in blended system is around 2%. So there's quite a significant jump by altering the process. I'm conscious of time, so just to capture is innovative manufacturing processes are here at Nottingham to make the CMCs, and suspension plasma spray is one of the unique ways. So that's the UK's only suspension plasma spray facility to make aerospace grade CMCs. And MMCs from cold spray is a new way of producing MMCs without going through the multiple stage process. It's a single step process. You can deposit it in less than 5 minutes. And a whole new range of composition and microstructures are available for applications like thermal barrier, environmental barrier, or electrical applications. Thanks very much for listening.
Thanks so much, Tanvir. Thank you. And thank you, everyone, So I'm sure everyone appreciated that. I'm a bit aware of time. I guess people might have other things to go to. So we'll go to the question and answer session. So I just really encourage people to either put their questions in the chat window, which is kind of in the little speech bubble you can see at the top of your screen, or just to raise your hand and unmute yourself, and please go ahead. So if the presenters can put their cameras on, just so that we can see one another, and I don't feel as if I'm alone here. Yeah, so please, any questions? I can see someone's got a hand up, so if they do, just please go right ahead. Ian, do you want to unmute yourself and just go ahead?
Cool. Can you hear me okay?
Yes, we can.
Cool.
Yeah.
Right. My name's Ian Lane. I'm from the Planet Airbus. I noticed you mentioned that other smaller commercial aircraft manufacturer a few times in your presentation, so I'll skip over that. It's just a question for Tom Turner, actually. I just wanted to sort of pick your visionary brain for a second. You made a very explicit statement that you said you can't recover continuous fibers. Is it we can't recover continuous fibers yet, or is that really like a absolutely there's nothing you can see on the horizon that might suggest we could?
Yeah, thanks for that, Ian. Sorry to cause any offence. Boeing have given us quite a lot of funding over the years, so you know.
Don't worry, it's perfectly humorous. We have a great relationship with each other. So please.
Yeah, it's a really good question. My feeling is that it's whether it makes sense to do it rather than whether it's feasible to do it. So you can take, of course, a roll of material, put it into one end of the process, and strip all the resin off that material, and then say, there we go, we've recycled some basically continuous fibers. It's whether really you can ever use those fibers for anything again. And my feeling is that you can't. You know, who's going to buy a 10-meter roll or a 50-meter roll of one material which shouldn't really exist in the first place? We don't really want to take fibers out of rolls of material. If I put a wing spar into a process, technically I could do the same and get continuous, 10-meter long fibers, say, but a lot of them aren't going to be that long. So what's the point of developing processes that, may be able to reuse those fibers? So my feeling is we need processes that are robust to take parts of all sizes, which probably means we do size reduction first. We run them through a recycling process, and then we develop tools to recycle that material into something we can use. So I think fibers over 25 millimeters are not so exciting. I guess there are some dry fiber processes that can reuse fibers up to about 100, but more than that gets very difficult.
Okay. Thank you. Cool. I just wanted to hear what was going on in your considerable brain about that. Thank you.
Right. Thanks very much, Ian and Tom. Do you have any other questions, please? Just raise your hand. Yeah, so Sarah's just said slides will be available. We've got another hand up from Frank Kirkland. Frank, please go ahead.
Yeah, so the question around BNNT materials and their applications. Mentioned using them with titanium and aluminium. What sort of maturity are those? Is that sort of experimentation at? Because obviously there's plenty of good applications as it matures.
I would say it's very early stages. We see the tremendous possibility. You see that some people have actually advanced it along in specific ways, but it really is. It's in its infancy. We don't want to oversell it, but it looks to have tremendous possibilities based on what may be done with it. Lyndsey?
Agreed. Sorry.
Okay, thank you. Very interesting talk. Thank you very much.
Okay, thank you. Thanks very much. I think there was a question in the chat, which I'm just maneuvering to. Excuse me. Yeah, so Steve Sapsford asked, excuse me, are there opportunities to combine the recovered carbon fibers in a metal casting like aluminium or magnesium? And how effective would that be in terms of material performance and cost?
Yeah, I guess that's one for me as well.
Yeah.
Yeah, I think so. It's not something that we've done anything more than think about. But yes, I think maybe there are some issues. Carbon is doesn't like high temperatures that much, as one of the presentations alluded to. So over 500 in an oxidative environment, things go downhill very quickly. So you'd have to be very careful. And you would still have the issues I was talking about with fiber packing and the sort of volume fraction addition. So one option would be, could you add a very, very low percentage of fibers just to do a specific job rather than to act as a structural reinforcement in the normal way? So a sort of crack arresting type process rather than a reinforcement as such. But yeah, it's a good question. Maybe we'll see some work on that at some point.
Great. Thanks very much, Tom, again. We've got a hand up from Norman Weaker. Norman, do you want to unmute yourself? Thanks.
Hello. Yeah. I've got a few questions, actually. I think the first one was an observation. Hi, Ian. It was a long time since we spoke. I think in
great to hear you again, Norman.
Yes. I think in aerospace materials, I think we're probably always doomed never to be able to use recycled materials, because material qualification pretty much needs to have traceability from from the mine to the aircraft. So trying to trace materials that are recycled is, I won't say impossible, but certainly adds quite a significant burden to knowing its provenance and therefore what its properties are. It's the repeatability of that material as well. So I just think that's probably going to be a little bit of a hurdle that will be hard to cross over. But I guess the next question is on the organisers, I guess, which is, it's good to hear about carbon recycling, but the ultimate recycling is something that is a natural product in the first place. So is there any sort of work going on in Nottingham in terms of the natural fibres, let's say hemp and other types of materials like that?
Yeah, so maybe I'll take that one. Not that I'm aware of at this stage, and it was actually a question I had for some of the speakers as well, if there was any work going on in that area. So as far as I'm aware, there isn't work directly on taking natural fibres and putting them into composite materials. There are people who are working on the sustainable chemistry aspects of those things, but I think it's not so much in the materials aspect, insofar as I'm aware. Maybe Lyndsey, Roy, or maybe Xianghui, do you know anything going on in that area, or Luca even? Are you aware of any use of natural fibres in making composites for, well, any kind of mechanical application, I guess?
I think it's probably from the paper, yes, but practically maybe not.
Right. Yeah.
Okay. I was aware of a company called Hemp Earth, which has made a light aircraft from hemp.
Yeah, right.
I just wondered if there's anything else, but thanks anyway.
Also from the message, just one question for me is about ice templating method. This is the method to try to produce the porous structure first, consists of this brown nitride skeleton. After that, we can do the next step, do the impregnation of polymer resin. So it's the resin it's free to choose for the second step, not one step.
Okay.
Okay.
Okay, thanks.
While you're on the topic, David, so we have got a colleague, Mike Clifford, whose specialty is natural material. So I think he's worked with wood and hemp into systems for polymers. So it'd be worth. I'm going to put his link in the chat, so anyone interested can have a look. Okay,
that's fantastic. Thanks so much, Tanvir. We've got a hand up from Paul Heathcote.
Hi, yeah, thank you. A sort of an observation, if I may, please, for Thomas, and then a question for Alastair, but from an operational perspective, Thomas, about 50% of aircraft damage to carbon fibre goes unreported. So it only happened during inspection processes. So I'm just wondering, in the context of trying to develop materials that we can sort of recycle carbon fibre through, where there's an opportunity to embed a different type of bonding material to the carbon fibre that aids the damage resilience, I suppose, or the monitoring, and at the same time aids its recycling capability. So I don't know, that's sort of like a statement, I suppose. But for Alastair, I was really interested on this hydrogen storage. I think it's such a big and interesting area. But how scalable is the modelling that you do? Does it only work on small vessels, or can you scale it up to sort of rocket-sized cylinders, that sort of thing?
Hello, sorry, let me take myself off mute. Yes, so we have done quite large-scale simulations, and we've also built what we would consider fairly large-scale prototypes. So we would handle maybe 1 kilogram of material in our prototypes, but our simulations have gone larger, and there isn't really a limit in terms of simulation. There are properties that will emerge that you won't get in the lab that you would have to anticipate on a larger scale. So you've got bed densification, and you've got the bed expanding with the cycling. So there are some phenomena which you won't be able to anticipate until you start building these systems for real. But in terms numerically, we have gone quite large. We've looked at sizable thermal storage using these hydrides for CSP applications. So that's up to tons of material. But again, it's all theoretical, and we don't really know in the physical world how things would respond. But there is really no limits in terms of scale when you're doing numerical theory. Yeah.
Okay, thanks very much, Alastair. We've got a couple of questions in the chat. So one is for Tom. It's from Ian Hamilton, and he says, we have similar challenges with recycling and aligning CF and other fibres using hyperdiff. At which TRL would you estimate your process at the moment?
Yeah, I mean, that's a good question, Ian. I don't think I would answer that, because I think TRL numbers are banded around a bit too casually. And, you know, there's technical feasibility, and then there's loads of other aspects that need to be considered. I'm aware of your work and the scale-up stuff that's going on at NCC. We're in a similar sort of place, I would say, and some advantages, some disadvantages to each process. So not too dissimilar, I guess. There's a non-answer for you.
Well, thanks anyway, Tom. There's a question from Kerry Vaughan. I guess this is for Luca. So Kerry asks, how well developed are the industrialized routes to deliver carbon fibers sustainably derived from acrylonitrile?
The short answer is work in progress. We have already run some projects in collaboration with OEMs in some areas. You know, looking at, for example, a biomass in US. It's still an area that you know, we're working on. We're clearly not ready to supply the market with a fully sustainable product. That would be the ideal scenario. But it's clearly one of our priorities going forward. To do all the limitation of the current you know, supply chain source and, you know, manufacturing method, which is definitely not ideal or fantastically sustainable.
Okay, great. Thanks very much, Luca. I can't see any other questions in the chat. I'm not sure. Paul Heathcote has his hand up, but I guess that's kind of a residual hand up there that he's just left up. I had a question for Roy and Lyndsey. I was quite interested in these composites where you have a very high loading, and you see that very enhanced effect when I think it was about 28%, if I remember rightly. So maybe for you guys and also for the other people, you know, I mean, what's the feeling for the loading of materials like boron nitride nanotubes or other materials in terms of their weight percentage with respect to the polymeric materials, whether it's epoxy or acrylonitrile or whatever?
I think it really depends on the application. For something like those high strength fibers, it's
Right.
got to be up. I think it's got to be up above 50% for sure. And I think there a lot of folks are headed in that direction. But you know, as a company, we're obviously interested in the ones that need tiny amounts of material. So that's why we're also looking at some of these thermal applications and other things too. Yeah.
Right. Okay,
Right.
that's good.
Yeah, exactly. And it's very different how they go in. Some things getting beyond a couple percent is very challenging, and others, you know, out the gate there you can see a path to 50% and above. So it's very application specific, and so we work with people who are truly in very different spheres looking at this.
Okay.
Yeah.
Xianghui, in your materials, what kind of loading is that at? I didn't catch it. If you
I
said
think it's around 20% volume fraction. So the density will be, I think it's below 3 or close to 2.5.
Yeah, okay. Thanks very much. There's a comment from Norman Weaker again. So maybe this is for Tom. We talk of recycling fibers, but what happens to the resin? Is this a problem? So I guess that's for maybe Luca and Tom, perhaps.
Yeah, I think it is a problem. We focused on recycling fibers because that's where the value is, and ultimately you need to generate some value to encourage people that it's worth even doing this recycling. So in the current recycling processes that are working commercially, they're basically pyrolysis processes, and the resin goes up the chimney and the fibers are extracted. There is a whole other class of process based on solvolysis, and we've done some work at Nottingham on that over the years, and then you can get some useful materials from the resin. So you might extract phenols and phenolic compounds from epoxy resin, but then you're back to this question about value and who's going to buy, you know, these materials which you can't really sell into other applications. So we're a bit stuck with the recycling the resin. I guess there is an opportunity for a fundamentally different resin chemistry, and there are people looking at that. But as we've heard, aerospace is very risk averse, and those are materials that aren't going to gain traction in the market without an awful lot of testing. So that would be my take on it.
Well, thanks for the answer. I think I'm not too sure that the aerospace is the right market for recycled composites, as I said. So, but possibly in tooling and things that go into the aerospace industry. Anyway, thanks.
Yeah, but that's why I think automotive is quite a good angle for this. Take the fibers from aerospace
Yes.
and put them into another market. I think you're
that
right.
makes more sense.
It's difficult to get them back into aerospace.
Yeah.
Yeah, and I believe the problem definitely won't go away. It's gonna just get worse and worse, and I think we're just at the start of the curve when lots of airplanes will come to their end of life. I think the problem will be big. I don't think they can fill deserts with decommissioned aircraft. I think something else will have to happen, of course, but it's not an easy one of something that for which we have technology ready today.
That's great. Thanks very much, Luca. There is a comment in the chat window from Ian Hamilton, which says we've used solvolysis with PP and PA6 to show repeated 5 times remanufacture testing using hyperdiff using recovered matrix fibers. So yeah, that was just a comment for those of you interested in that area. Yeah, there's a comment from Norman again. Just bear with me. Oh, thanks very much. Thanks very much for attending, Norman. Thank you. So I don't know if anyone else had any other questions. I'll just wait maybe 10 seconds to see if a hand goes up or someone unmutes themselves. I'm aware we've gone over, so I really appreciate everyone sticking around and going over, and apologise for the technical issues again. but it's hugely appreciated. I'd like to thank you all for your presentations. It's fantastic. So if people want to unmute and applaud, please feel free, because it's the only way I can think of to do that. So if you want to unmute and applaud, I'll applaud anyway. So thanks very much, everyone. I think it's a great afternoon.
Thanks, everyone.
I hope you made some good connections, and yeah, look forward to working with you all again sometime, I hope. All right. Thanks very much, everyone. Have a good afternoon.
Thank you.
Good morning, Roy.
Thank you. Bye.
Bye.
Thanks. Bye-bye.